In this screencast, I'm going to introduce you to a new distribution, the F distribution, and I'm going to show you how we can use the F distribution to perform hypothesis tests related to the comparison of two population variances. From previously, when we were talking about comparison of means, we had to make the assumption that the population variances were either equal or not equal. For example, we worked through this natural gas example. We determined the standard deviations to be 5.2 and 4.1, and we just assumed that those are pretty similar. We assumed the variance equal case. But now you're going to learn how you can show statistically that the variances of the methane concentration are equal or unequal. Again, recall that we had to make the assumption that the variances were equal or not equal, and that guided us to which test statistics to use in the comparison of means scheme. In order to compare variances of two populations, we use the F distribution. The random variable F is defined as the ratio of two independent chi-squared variables, each divided by its degrees of freedom. Here, W and Y are both chi-squared random variables, and U and nu are the numerator and denominator degrees of freedom, respectively. The associated probability density function of the F distribution is shown here. It's quite complicated, and again, like the other probability density functions that I've shown, it's not important that you memorize or can use this as written because there are Excel functions and tables out there that give you the data related to the F distribution. The F distribution has an asymmetric shape. Here we have one example. I've also got this file on the course website where we can change the numerator degrees of freedom, U, and the denominator degrees of freedom. That's what the F distribution primarily depends upon. And you see that if we change those degrees of freedom in the numerator versus the denominator, we can change the shape of the F distribution a little bit. The F distribution doesn't change too much, but it does change a little bit, and it's always quite asymmetric. Just like the other probability density functions we've been working with, we can denote a point on the abscissa that corresponds to the area to the right when we have that in a subscript. So here, if this is the F distribution, F of alpha with U, numerator degrees of freedom, and nu, denominator degrees of freedom, we can denote that as F alpha U, comma nu, and that has alpha to the right. If we wanted to denote the F value having alpha to the left, that's F of 1 minus alpha with U, numerator degrees of freedom, and nu, denominator degrees of freedom. And just because of the nature of the mathematics behind the F distribution, this is also equal to 1 over F alpha of nu, comma U. You notice here that we have switched the order of the numerator and denominator degrees of freedom. This used to be quite useful because tables in the back of your book and elsewhere would only publish small values of alpha. In other words, they wouldn't publish F of 1 minus alpha. If we take a look at your book, table 6 in the appendix A, you see that there's different tables depending upon what alpha is. So here we have alpha equal 0.05. The next page is 0.025 and then 0.01. But we never have left-tailed distributions. For example, F of 0.99 with nu1 and nu2 degrees of freedom. Nu1 and nu2, by the way, corresponds to U and nu that I'm using in my terminology in my PowerPoint slide. By the way, there are Excel functions that do this, f.dist. This gives the cumulative probability. F.inv gives the F value for a given cumulative probability P. And so we can easily use Excel to determine these percentage points of the F distribution. And they depend upon two degrees of freedom, the numerator and denominator degrees of freedom. So how do we use this for hypothesis tests when we want to compare variances? Well, the ratio of sample variances follow chi-squared distributions. So an F distribution we can set up as follows, where the samples have to be both normally distributed. The random variable F is described by an F distribution with n1 minus 1 numerator degrees of freedom and n2 minus 1 denominator degrees of freedom. Typically, the null hypothesis is that the variances are equal. If that's the case and the variances are equal, then these basically cancel, and our test statistic is just the ratio of the sample variances. And then we can perform a hypothesis test on this. For example, if our alternate hypothesis is that the variance of population 1 is greater than that of population 2, this is an upper tail test, and in order to accept the alternate and show that the variances are not equal, we can compare our test statistic to F alpha N1 minus 1 numerator degrees of freedom and N2 minus 1 denominator degrees of freedom. And the rejection criteria for the null hypothesis, acceptance criteria for the alternate are similar to what we've done previously. We can calculate for a two-tailed test. In order to accept the alternate, the test statistic has to be greater than F alpha over 2 or less than F of 1 minus alpha over 2. And again, note that we can always compute F of 1 minus alpha over 2 by the reciprocal relationship where we're switching the order of the degrees of freedom. For an upper tailed test, our test statistic has to be greater than F sub alpha. And for a lower tailed test, our test statistic has to be less than F of 1 minus alpha, or equivalently, we can use the reciprocal relationship, and our test statistic has to be less than 1 divided by F of alpha, and we've switched the order of the degrees of freedom there. So let's revisit our example. We're going to be doing an upper tailed test because our sample standard deviations suggest an upper tailed test. And we're going to calculate a p-value for this test. First, we need to calculate a test statistic. That's just the ratio of the sample variances, S1 squared divided by S2 squared. So the ratio of our sample variances here is 1.58. That's our test statistic. And now what we need to do for an upper tailed test, we're comparing to F of alpha with 6 degrees of freedom in the numerator and 4 degrees of freedom in the denominator. So we can compare this to the F alpha, F.inv. This is going to be a right-tailed function. We're going to put 5% into the right tail. Numerator degrees of freedom is N1 minus 1. Denominator degrees of freedom, N2 minus 1. And that's 6.16. We would have to exceed that value, that critical value of F sub alpha that has 5% to the right of it, but we are not exceeding that. And so our conclusion is that we cannot accept the alternate hypothesis and we fail to reject the null. And so in this case, we would assume that the variances are equal. Now let me show you how we can use the data analysis tool. If you go into data analysis, and you select F-test, to sample for variances. We can click OK. It asks us to input our variable 1 range, so that's our source 1. Our source 2 is that. Our alpha is 0.05, and let's just put this onto the spreadsheet over here. I'm just going to select in cell H8, and we run that, make this a little bit bigger, and we see that the test statistic that we got is what that tool got. The to sample for variances data analysis tool obtained. We also get the critical one tail F value here, 6.16. And let's real quick calculate a p-value. So we can use the f.dist. This is a right-tailed test because this is an upper-tailed. Our test statistic of 1.58, we had N1 minus 1 numerator degrees of freedom, N2 minus 1 denominator degrees of freedom. And when we press enter, we're getting a p-value of 0.342, which is what that tool gave us as well. Our conclusion then is that we cannot accept the alternate, and we assume that the variances are equal. And that's what we would use then. If we go back to the comparison of means scheme, we would use the variance equal case. Hopefully this screencast gives you a better idea of the F distribution and how we can use the F distribution to compare variances of two populations.